Welcome back to the Explainer. Today, we're diving into a fascinating 2026 research paper by Vladimir Kasia. It's called Memory Efficient Exact Backpropagation, Shattering the Computational Graph. And honestly, this is a method that promises to completely rethink how we handle memory and AI training. It's a really exciting concept, so let's just dive right in. Look, if you've ever tried training a deep neural network, you've probably found yourself staring down a devastating out-of-memory error. It is incredibly frustrating, right? The hardware limits of artificial intelligence can be brutal. So, to really appreciate Kasia's solution, we first need to confront the core problem. What is fundamentally constraining modern deep networks? Well, as we build these large language models with massive contexts and gigantic vocabularies, the hardware requirements have basically become this Goliath that we have to defeat. I mean, we're talking about hundreds of gigabytes of memory just to train the models that we interact with every single day. The standard approach requires caching massive amounts of intermediate data during the automatic differentiation process. It's kind of like trying to memorize every single step, misstep, and rough draft of a novel while you're still in the middle of writing it. It's exhausting. And this AI memory bottleneck isn't just some random hardware quirk. It's a harsh mathematical reality. Standard automatic differentiation actually forces your computer's memory to carry this massive, super heavy, monolithic computational graph all at once. The memory footprint scales linearly with the number of network layers, which we denote as L, the batch size B, and the sequence length T. And on top of all that, evaluating the final predictions against the entire vocabulary introduces this massive spatial lower bound. So the larger your model and your context, the heavier this graph gets, which completely restricts the batch size you're allowed to use on any given GPU. Okay, the contrast between the old way and this new approach is just super fascinating. In the standard setup, we have the global computational graph. That's our current reality, where absolutely everything is cached, resulting in that huge memory footprint we just talked about. But Kasia proposes something radical, the shattered graph. What if we explicitly abandon that global graph? Instead of holding the whole network in memory like a giant monolithic block, we decouple it. We isolate the math to just a single architectural block at a time. By shattering the dependencies, we can drastically, and I mean drastically, drop the memory requirement. Now, the result of that shattered graph is this new mathematical formula for spatial complexity. I know. It might look a bit like alphabet soup at first glance, but let me tell you, to a machine learning engineer, this formula is absolutely beautiful. It represents a really aggressive way to prune the dependency matrix. By discarding those unnecessary high-dimensional intermediate states and actually limiting peak allocation, the memory overhead associated with the vocabulary, that V you see right at the end there, is massively reduced. It literally changes the scaling laws for training on a single GPU. So how does the data actually travel through this shattered setup? Kasia breaks the gradient computation down into 3 distinct mechanical phases without ever constructing that global graph. First up, we have the primal sweep, then the shattered boundary condition, and finally, the backward block sweep. Honestly, think of this like the ultimate logistics operation. Rather than trying to move a whole warehouse of goods all at once, we're moving only exactly what is needed, precisely when it's needed, and we're tossing out the packing materials immediately. All right, let's break down phase 1, the primal sweep. This is where we immediately drop the heavy load. Normally, a forward pass evaluates and saves, well, everything. But the primal sweep, it evaluates the forward dynamics, but flat out refuses to track the full graph. Instead, it pushes only the necessary boundaries, the states strictly between the network layers, into a static memory stack. It explicitly throws away all that intermediate attention logic and feed-forward activations. We are keeping only the absolute bare minimum checkpoints needed to reconstruct the path later on. Moving right along to phase 2, the shattered boundary condition. This one tackles the vocabulary memory bottleneck. Evaluating the terminal cross-entropy normally requires a massive, full tensor over the entire vocabulary, which is incredibly heavy. But Kasia's method brilliantly isolates this high-dimensional projection by breaking it down. It evaluates the terminal cross-entropy iteratively, over much smaller micro-batch chunks. By shattering this projection over the batches, the memory requirement shrinks from scaling with batch size, sequence length, and vocabulary, down to a highly manageable requirement that scales only with sequence length and vocabulary. It's a real game changer. And that brings us to phase 3, the backward block sweep. This is the part where the gradients move backward to actually update the model, but remember, we don't have a global graph anymore. So the algorithm just reconstructs the local forward transformations sequentially one block at a time. It grabs those boundary states we saved back in phase 1, does the math, the vector Jacobian products, and then explicitly deletes or dereferences that local graph before moving to the very next block. Because of this, the peak dynamic memory allocation never ever exceeds the bounds of a single architectural block. Okay, so the theory sounds incredibly elegant, right? But does it actually work out in the real world? Kasaya set out to prove this David mathematical approach against the Goliath of standard training using hard data. For the experimental setup, they used a 60 million parameter causal transformer model with grouped query attention and trained it on the ultrafine web dataset. And honestly, here is the kicker. This was all executed on a single, pretty standard 16GB NVIDIA T4 GPU. No massive server farms, just one totally accessible graphics card. So, what was the result? A massive 62.9% reduction in peak video RAM. Yeah, you heard that right. By explicitly avoiding the global computational graph, the memory footprint was literally slashed by more than half. This is a staggering drop. It radically frees up the hardware to potentially handle much larger batch sizes or sequence lengths than anyone ever thought possible on a 16GB card. When you map out the training loss over 1,000 optimization steps, the trajectories overlap perfectly. The standard baseline and Kajia's shattered method are entirely indistinguishable. And this is absolutely vital because it proves the math is exact. We aren't just estimating or losing quality here. But the really wild part is the VRAM usage. The standard baseline spikes to and maintains a peak VRAM of 6.45 gigabytes. Meanwhile, our shattered method stabilizes at just 2.39 gigabytes. That is a dramatic and completely sustained drop in the memory ceiling. But training loss is only half the story. We got to make sure the model is actually learning and generalizing to new data. Well, when we evaluate the validation loss on a held-out dataset, the trajectories are, once again, perfectly indistinguishable. The baseline finishes with a validation perplexity of 125.82, and the shattered gradients method finishes right there at 125.21. The learning quality is 100% untouched. You're getting the exact same optimization trajectory, but achieving it with a fraction of the memory. Naturally, you're probably thinking, okay, what's the catch, right? If we're saving all this memory by recomputing things layer by layer, surely it takes way longer to train, doesn't it? Actually, scratch that. It doesn't at all. The standard baseline processes 3,380 tokens per second. The shattered gradients method, it processes 3,350 tokens per second. That is a completely negligible throughput drop of just 0.9%. The computational overhead is practically invisible. The algorithm manages to maximize hardware utilization without heavily taxing the processor time. Let's quickly summarize what this all means for us today. This algorithm completely avoids the construction of those massive global computational graphs. And because of this structural decoupling strategy, it cuts peak memory allocation by nearly 63% on this architecture. Best of all, it does all of this while maintaining analytically exact loss trajectories, so the model learns exactly as it should, and it incurs a nearly zero-cost penalty to training speed. We've effectively traded a devastating hardware bottleneck for a massive, massive gain in efficiency. Which brings us to the real ultimate takeaway here. Kasia actually refers to this as expanding or functional batch size elasticity. Because we're lowering the memory floor so drastically, we are no longer instantly bound by our GPU memory limits when we want to increase context length. So I'll leave you with this thought. With this exact decoupled backpropagation, how is this going to change the future of large language model training on limited hardware? Could this be the key to truly democratizing AI, allowing smaller labs and independent researchers to train massive models right from their everyday desktops? It's a fascinating paradigm shift for sure. I highly recommend digging into the source material if you want to explore the math further. Thanks for hanging out with me on this explainer, and keep learning.